Okay, so we're going to carry on with functions in 3-space here and talk more about this partial derivative with respect to x and y. And so this is the picture from the last video here. And so just to recall here, here's some surface z equals f of x, y, and then we pick some point x naught, y naught, and we fix the plane through y naught. So y equals y naught is fixed. All right, so that means we're fixing y, and x is going to move. And so if you project this point up, this gives you the point. We'll call it P x naught, y naught, f of x naught, y naught. So here's this point. Here's this point on our surface, and the tangent line that's parallel to the x-axis looks like this. All right, so this is the line. I'll call it L1. And L1 is the tangent line to the surface z equals f of x, y at the point P. So in the x direction. The slope of this line is, okay, it's the partial with respect to x evaluated at the point x naught, y naught. I'm going to call it z naught, right? Which is actually, I'm going to take that out of there. Shit. Faster. It's just, and there's another way to write this. So just like we have the d dx and f prime of x, we have now, if we're taking the partial with respect to x, you go f sub little x of x naught, y naught. And so these are two different ways of writing the same thing. And we can do this with respect to y as well. Everything is turned 90 degrees. So for now, let's just focus on the partial with respect to x. Okay, so now this is key. Okay. When you compute df dx, you hold y fixed. And this does a number on your eyes because you're used to thinking of y as a variable, but you really want to think of y as a constant. Pretend it's the number 2. Okay? And then you just do all the differentiation stuff you've been doing since Calc 1. So, for example, let f of x, y be the function x squared plus 3xy plus y minus 1. And 1, we're going to compute df dx, or you could write it f sub x. Right? Okay, I'm going to get to the top of the screen here. All right, so writing down all the steps, I'm looking at the right-hand side of this equation. So I take the derivative, the partial derivative with respect to x of x squared, plus the partial derivative with respect to x of 3xy, plus the partial derivative with respect to x of y, minus the partial derivative with respect to x of 1. Okay, so now if we're taking the derivative with respect to x of a function of x, you just do good old calc 1. The derivative of x squared is 2x. Okay. This guy is a little complicated, so I'm going to save it. We'll do that one last. So I'm just going to leave that operator sitting there. All right, now this is key. This is the key step here. Okay. In this game right now, y is a constant if you take the derivative with respect to x, so this value is 0. And similarly, the derivative of a constant is also 0. Right? And that's new to us. You don't normally take the derivative of a variable and have it be 0, but because we're taking it with respect to x, we get 0. So it's treated as a constant. Okay. So now we're going to deal with this fella, right? So just like before, the 3 comes out front, and I need to use the product rule. So I fix y and take the derivative with respect to x with x, so that's y times 1. And then I fix x and take the derivative with respect to x of y, which is 0. And so my final answer is 2x plus 3y. Okay. Going through all the grisly details. Okay. So now we found df dx for this function, or f of x. So I'm going to write it like this. I'm going to say f sub x of x comma y is 2x plus 3y. There we have it, right? Okay, let's do this with now df dy. Now we're going to hold x fixed. Okay, so writing out all the steps, I said df dy, and I wrote df dx. So this is supposed to be, sorry about that. This is supposed to be df dy, because we've already done df dx. So now we're doing df dy. Okay, so running through all the steps, we go the derivative with respect to y of x squared plus derivative with respect to y of 3xy plus the derivative with respect to y of y minus the derivative with respect to y of 1. Okay, so I want to put compute here. Okay, so now this is equal to, all right, so now x squared, or x, anything with an x in it and nothing else next to it, is treated as a constant. So that derivative is 0 plus 3. And so, all right, the derivative with respect to y of x is 0 times y plus the derivative with respect to y of y is 1, so we have 3x. Okay, and then the derivative with respect to y of y is 1, and then that's 0. So we're left with 3x plus 1. All right. So being official here, so the partial with respect to y of this function is 3x plus 1. Okay. All right, well, that was fun. And it's as easy as you think it is. You just have to remember when you're doing this, which one you're actually working on. So if you're computing df dy, remember that x is fixed. And if you're computing df dx, remember that y is fixed. Everything else, so all Calc 1 rules apply. Chain rule, product rule, quotient rule, power rule, it's all in there, okay? As well as implicit differentiation rules apply. And these help so much. Okay, so let's do a little example here. So let's consider the equation yz minus ln of z equals x plus y. And we want to find the partial with respect to z, with respect to y of z, right? So remembering how implicit works, we can't solve for z explicitly. So you can't get z as a function of x and y only. The ln of z screws it up. So you have to leave this as an implicit function. Okay? And so I didn't want to put, hold on, this is supposed to be dz dx. We're going to find dz dx. Okay. All right, now you just have to think implicit and partial at the same time. But it's not the end of the world, right? So here's what we do. We use the operator d dx. And as I'm teaching, I'm going to write out all the steps. So now I'm computing the partial with respect to x of the first term yz minus the partial with respect to x of the second term ln of z, which is equal to d dx of x plus d dx of y. Okay, now note this says y is held constant. Why? Because we're taking the derivative with respect to x. And that says y is held constant. And z, so that means we assume z is a function of x in our implicit. Okay. All right, let's do this. So our first move here is to compute, let me get some red in here. I like the red. Oops, come on. This guy. Okay, well, look at that for a second. Y is held constant, so it's actually y times d dx of z. All right, so all I did in this first move was I pulled the y out front because it's a constant, okay? Minus, back to red, this guy. And here's the implicit piece. Remember how the implicit works. You pretend that you're integrating with respect, you're differentiating with respect to z, so it's, come on, 1 over z times dz dx. That's really ugly. One over z times dz dx. And okay, let's look at this guy. So the derivative with respect to x of x is 1, and this guy, the derivative with respect to x of y is 0. Okay. All right, so we have one more derivative to do here. I am taking a lot of steps, but I think it's important. So now this becomes y. So the derivative with respect to z of z is 1, but then we pick up dz dx by the implicit piece. One. And then so then we factor out dz dx, which is what we're solving for. And we get y minus 1 over z. And all that equals 1. Okay. And then so that says that dz dx is 1 over y minus 1 over z, which is 1 over, what is that? yz minus 1 over z, which is z over yz minus 1. Okay. And that's the final answer. Okay. So yeah, that's an example. It's a pretty hard one of how implicit works with differentiation. You just have to keep your variables straight in your head, and the chain rule helps a lot. Okay, so let's do some applications here. A little example. In black, yep. So we're going to let z equal x squared plus y squared be a surface. It's actually called a paraboloid. We'll talk about these particular names and later on, but for right now it's called a paraboloid. Okay, and then we're going to let x equal 1 be a plane. Okay. Now the plane, the plane intersects the paraboloid, it cuts it. And when it cuts the paraboloid, it makes a parabola through the plane x equals 1. So this intersects the paraboloid and makes a parabola lying on the plane x equals 1. Okay. And on this intersection lies a bunch of points, infinitely many to be exact, but one in particular, 1, 2, 5, that lies on this. On this intersection. Okay, and we're tasked with finding the tangent line along this plane at the point 1, 2, 5. Okay, so I'm going to do my best to get GeoGebra to give this picture. Come on. So I hold this. This guy comes over like that. Go away. I want this to go away. Delete. So it's going to be, oops, x squared plus y squared. This guy needs to go away. I said go away. There we go. So there's the paraboloid. And let's see if it shows the plane. It will. X equals 1, right? So let me see if I can't move this. That's pretty good. And let's go ahead and put the point 1, 2, 5 in there. So how about if I make it even bigger? Oops, stop. Bear with me here. Stop. You go away. There we go. Okay. Trying to get the right. So yeah, if you look at that, you see there's the paraboloid, and then that blue thing is the plane. And along that plane where it cuts the paraboloid, there's the point 125. It's in blue. And the idea is there's a tangent line through that point that we want to find, and we will find it. So I'm going to get rid of this guy. Come back. Is that it? Yes. Okay. All right. Okay, so the key here is that the slope of the tangent line. Are you on? Yep. The slope of the tangent line is dz dy evaluated at 1, 2. Why? Because remember, x equals 1 is fixed. That's the fixed plane. So all the derivatives are moving, well, the derivative is moving in the y direction. So we need to find dz dy, which is pretty simple, I think. Sure enough, yep. If you look back up here, the derivative with respect to y of x squared is 0, and the derivative with respect to y of 2y of y squared is 2y. So we evaluate that at 1, 2, and we get that 4 is the equation of the tangent line. Sorry, it's the slope of the tangent line. Okay, so here's where it gets fun for me, and hopefully for you too. The equation of a line in three space looks like this. It's x naught, y naught, z naught. Oops. Let me erase that. It's x naught plus tv1 tv2 plus tv3, where what? v1, v2 is a vector parallel to the line. Okay. Oh, I should have done this before. All right, we're going to go back and look at this. I can do this. I'm confident. Come on. Hold it. Move over. So unfortunately, I can't mark on this because it's actually a website. But if you look at, can I draw on here? Yep. If you look at the parabola, up here is the point 125. Here's the origin. What we want is the vector through there. And if here, let me turn this a little bit. If you think about this, what's that vector? The vector v is j plus 4k. Right? Because if you turn it like that, this is the YZ coordinate planes you're looking at. X equals 1 is perpendicular to us. And so what the slope is up 4 to the right 1, and so that vector is just j plus 4k. So there's the vector. Okay, go big. All right. Okay, so let's put it all together. The line is, how do I do this? It goes x equals 1 plus 0t, y equals 2 plus t, and z equals 5 plus 4t. And so just to clean it up, 0t is 0, which makes sense because x equals 1 is fixed. Okay, so let's go. I keep doing this. It's all right. Let's go back. No, that's not what I wanted. Fuck. I don't know how to undo that. That's not what I wanted. Oh well. There it goes. All right, I got it. Let me do it again. I'm going to put everything back in again because I want this to finish properly. So x squared plus y squared and the point 1, 2, 5, and then I'm also going to add the vector 1, 2 plus t, 5 plus 4 t. Okay, so stop. So there's our tangent line to the point 125 on this surface. And it all worked out beautifully. You can see it only touches in one point there. So, all right, a few hiccups, but getting better. All right, and actually later on we'll find an even easier way to find those tangent lines. But for now, this is the best we can do. We don't have directional derivatives yet, so. Okay, so homework time. Homework time. Let's see here. This is homework 5. Can't believe we're a third of the way through the semester. This is due Monday at 4:20, right? (1620), and it's sections 14.1, 5, 10, and 11, and 14.3, 1, 4, 8, 11, 24, 40, 44, 53, and 65. It's a very dense section. And this is all I'm assigning. So it's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 problems for the week. And yeah, if you did a couple of these before Friday, we have something to talk about, but understand if you're busy. So that's it. I'll see you all in a little bit.